I just want to remind you that the lectures should be available. Already I uploaded the lecture. If anybody wants to actually watch it again, alright, it should be available here. Alright, let's take a look. Yeah, it should be. Yeah, it is available. Okay, yeah. Alright, so yeah, it's and the playlist is actually here, right? The Ortus in the beginning, right? This playlist here. We'll take a look if it's actually still live. Yeah, and it has all the lectures here. Okay, right. So we are at the what's that sound? Is that a speaker? I don't know. That's a conditioner. All right. So yeah. So we are back at our power function. And this one is supposed to be better, right? This one should be better, right? At least intuitively, yeah. It should be doing less work, right? Again, it's still not perfect, far from being perfect, but at least it should be more efficient, right? So we tested it works, right? We can do 10,000. It works. Now we can do mass, right? Import mass on 10 log, right? So the idea is to get 10,000, we should be making about 14 calls. Okay, but let's test it actually, right? If you have a 2 to the 10,000, right? Actually, we're going to be splitting it down to about 14 levels, all right? So what does it mean actually, right? Because we are splitting to 5,000, 2,500, 1,250, and so on, 640 something, and so on and so on. So it goes down very quickly. Now, how to prove it to you? I'll do again verbose. I'll do a verbose function of this. Let's do a verbose version. Let's add. Let's make a verbose version. Let's make a make this same function with verbose flag. Okay, power. I want power verbose, not power verbose. Yeah, so verbose. Let's take a look. Test it. Yeah. Oh, power verbose. What's the oh yeah, of course it's verbose. What's the problem here? Oh. Because I'm calling the wrong function, power verbose, right? Yeah, of course. So I was calling the other function. Yeah. So you can see 1, 2, 3, 4, 5. Actually, well, 0 case 2, right? But basically, yeah, we had 4 calls, right? 2 to the 2 to the 1, to the 2 to the 3, right? So 4 calls here, right? Technically, right? So it's obviously less than 8. Right, obviously less than 8. So let's test it here for the 10,000. Right, it works. Let's do it. Let's do a verbose version. Let's do a verbose version. Let's see. That's scary. I mean, I could be getting 10,000 prints, right? But I shouldn't. Yeah, you see. So I go down, well, again 0 as well, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, 13 is really where the work is done, well, plus 2 more, right? A little bit of overhead, right? But technically, basically, right, we are getting very close to our log n complexity, right? For 1,000, right? Or 10,000 actually, 10,000, right? So for 10,000, about 14 calls, right? So again, so hopefully you can see this should be more efficient, right? So let's time it. Obviously, we should time it, right? So Google, right? Large numbers, right? So we could even do it down to even I don't know very low. So let's test it. So 1,000. Microseconds already, right? So if you remember, our original was how much? Was like 300 microseconds, right? So about 100 times faster. So this version is already 100 times faster, than our original version, right? And obviously, so it should be, well, it's not going to beat the optimized version, right? But it should be close, right? It's about maybe 3 times slower, right? So let's do it for a larger number. Well, of course, again, we see this is the original is bad. Basic power is like, yeah. So now let's do 10,000, I think. Let's do 10,000. No, well, let's do, see. Let's do 2,000. So 4 microseconds. So this is going to be 2 times more. Yeah, about, well, 4 nanoseconds, right? So, and we can do even silly thing. Yeah, so this is this call, we could not do it with our original naive power, right? 2 million, right? 2 to the 2 millions, there's no way we could compute it because our recursion limit was 500,000. We just ran out of stack space, right? So 2 million. Welcome back. So 8 milliseconds. I mean, pretty respectable considering how large a number it is. 2 to the 2 millions. That's going to be about 600,000 digits. Pretty long number, right? Pretty large, right? Way beyond the atoms in the universe number, right? So yeah. So also things also where sometimes slowness or complexity hides is in these actual side effects, meaning like for printing out or dealing with these large numbers, there's actually, of course, overhead for dealing with these numbers, right? If you're only dealing with small integers all the time, right, you're not going to see this. But you're actually dealing with number with 600,000 digit number, right? It actually gets kind of messy to deal with that as well, actually. So there's some slowdown in it too, right? So, but yeah, we can't even calculate how many digits we have. Yeah, it turns out Python does not support converting digits to strings over 4,000, right? So I can't even see how long it is, but it should be about 600,000, right? Yeah. Oh yeah, I can change that actually, right? Yeah. And now let's see. Yeah, let's try it. Yeah, this is I tried last time. So you can set it and say, okay, yeah, I want to convert truly large integers to strings. Million. Let's do a million. Now I can see it should be 600,000. Yeah. Okay. Right. But again, everything again. So takeaway from all of this is that dividing problem space in half and half and half, right? That is always going to smell like log complexity somewhere, right? And that's usually but something you should strive for. It's possible, right? Now, right. So now what else can we do with this algorithm? We can time it, right? Occurs 2 to the million, right? 8 milliseconds. These truly large numbers, right? But now the question is, can we actually do math to the power of 2000? Let's time. Yeah, there's also a built-in. How fast is this one? Well, math to the power is 200 nanoseconds. So that's actually even more optimized, actually, math power. But if you remember, math power is actually gives you a float, right? This supports floats, right? So how could we make our own function support every digit, right? We have negatives, and because if we don't make this complete power function, what are some ideas? Like right now it only works on positive integers, right? Well,
I mean, for negatives,
yeah,
you just take the
yeah,
result and 1 divided by
yeah, exactly, right. So if it's like minus, exactly. So that would be one way of doing it. I think that's actually be completely a good approach to start with, right? Because we don't know the actual for doing the floats or the partials, right? Rational number, you know, like 0 point square roots and things like that, right? The algorithms for that are actually relatively complicated, right? They use Newton approximation, right? It's kind of funny, kind of cool algorithms. Maybe if we have time later on, we can look at those someday. But it's not something we will do today, right? So what we could do is we sort of cheat a little bit. We'll take from 0 to 1, use the actual built-in algorithm, right? And the rest we will just we'll reduce basically. So unlike your idea, minus for negatives, we just reverse it, right? we do the conversion basically. Okay, so let's do that. Let's do that, and I think I should be able to do it very quickly, right? Yeah. Now, power, right? So before that, oh yeah, we will plot also. We'll get a plot of these, but first let's make a complete power function that also works on negative powers. Let's see that. Let's see if AI does this for me. I'm lazy. Full power, NX, right? Right. It's thinking. Okay, let's take a look if it picked up on your idea. It should, but let's see. Did it cheat? I don't think it did anything here. Did it do anything? Let's see. Base case. Looks like it didn't do anything here. Unfortunately, AI didn't do the work for us. So remember, what we could do is basically, let's see, how could we handle this negative case? At which step do we want to do it, right?
At the end, when it returns results,
yes, that would be here, right?
at the very bottom.
Yeah. So let's do one more check, right? If x, yeah. No, that's not it. Or actually, well, x to the n. Actually, well, x to the n doesn't matter, right? Doesn't matter. But so x less than 0 and it's odd. No, that's not it, right? No. AI is missing today, so no. This means if x is less than 0, so for n, wait, sorry, oh yeah, no, if n is less than 0, right? Yeah, that's what I wanted, right? Okay, now this looks good. Now the only question is if it is okay. It looks good, but I have a feeling that it will go forever. I have a feeling this. Let's take a look at this now. Full power, right? This part here, right? We divide by 2. Okay, let's try some negative numbers. Let's try these positives. Assert it works, right? This should work, but 9 will work, right? But yeah, but that's not what we really worry about, right? These are the easy cases, right? No negatives, no negative, no negative. Yeah, I think it will not work. We'll have a forever loop. This should be half, right? This should be, of course, 2 to be 0.5, right? Yeah. And this should be 0.25, right? Not 10, but no, let's do 10. No, let's minus. Let's go -2. Yeah, this should be 0.25, right? Okay, but I have a feeling it might not work. It might not work. Why? Or maybe it will work if it divide. It keeps decreasing. We'll see. I think we'll have a session error. Yep, we got a session error. 0 division error, right? Yes. Negatives, right? So we got a negative error, right? Yeah, this assertion fails. Partial, right? So let's take a look what the problem is. All right, this part here. Well, first of all, this should work, right? Oops, sorry. Escape B. Okay, here. So let's check. This should work if I remember correctly. It works. Yeah, 0.5, right? On 2 -2. Yeah, works. Okay. Right. And so 4, 3, and 4, right? Yeah, okay, it works fine. Okay, now, so that works, or function doesn't work, right? So this part here, we need to do a little thinking about this a little bit. So if it's less, we return the reverse. That would be fine. But we start with a negative, right? And we call it here. So this is a part here. What happens here? Ah, result is 0 somehow, somewhere. That's interesting. Why are we getting 0? Ah, because I think. Oh, here's the problem. Yeah, x and n. Yeah, because originally I'm the wrong. I had switched x and n or vice versa. Okay, let's try it one more time. Okay, now it's worse because what we got infinite. We have infinite loop, right? Or recursion. It eventually should run out of recursion, right? Eventually, right? But yeah, but we set our 500,000 limit, right? So it might take a while, and I'll have to stop it. Yeah, keyboard interrupt on. Yeah, so that's the problem with recursion, right? If you do it incorrectly, in this case, our base case is not sufficiently defined. I mean, it seems like it's not getting to this 0. So let's take a look what's happening here. Why are we not getting to 0 eventually, right? So let's test our. So now let's see what happens when we divide a negative integer using, yeah, so minus, yeah. Let's try, we're doing by 2, right? So minus 1, right? Yeah, let's try this. Okay, minus 1, minus 1, and minus 3 gives you 2, you see? All right, not a problem. So we'll keep going towards negative infinity, right? Yeah, so how could we fix this? Let's see, we should be able to fix this. There could be, again, do some quick and dirty solution, basically, right? We know we should maybe do it earlier, basically, right? This negativity, right? So, or, again, it's obviously not going to be as efficient. We're going to have some extra ifs, but we can do this full power right here. It's correct, but we might want to add it here. That seems like this is a problem. We want to go down to 0, right? Right. So what we want probably is we want to check this negative, right? If, yeah, check if n is negative. So let's see. Is this interesting? No, that's no wrong. That's wrong. You see, you can't. It's that's you see, no. And then no. Then we have what? Then we have partial.
Shouldn't we send the partial instead of returning?
Do you mean?
Well, you just deleted the if statement, but it's returned the full power.
Yeah.
Shouldn't we return the
Partial. No, we want. Okay. No, the idea is we're not going to mess anything too much. We basically idea is the only problem is right now that when we're dividing by 2, right? It's flooring it basically, right? So yeah.
You know, we could just at the very beginning, if n is negative, just make it positive.
And that's it.
Take a modulus of n.
Yeah.
Because anyway, at the end wait, but we have to remember what it was for.
Yeah, that's the issue. You see, if we start this always, we make it positive, right? Then we'll lose this information, right? So it's a little tricky. So well, one way we could do it, of course, we could pass that this. We could of course make a flag, right, and pass this flag. Original was a negative, right, and then you should remember it, right? Yeah, it's a little bit tricky, right? But I think let's try this, right? This is going to be like a fix, right? That it's if it's this part here, we need to fix the basic only thing this part here, right? If negative, right? Next number, right? Next n. If next n. No, next x equals x, right, 2, right? No, basically this, if x n less than 0, right? Now again, next x yeah, equals, no, x, we'll do this. We'll cheat. I'm lazy right now. I'll do the full +1, right? That's all I'm going to do. I mean, it's basically ceiling, right? Otherwise, else, we'll see if this, I don't know if it's going to fix. Next x equals x divided by 2. Basically, that's it, right? And then I can add this one here, right? See if this solves the problem. Yeah. Let's see. Wait, or comma, or is the x or power n? It should be n. No, boy. What's going on? It should be nx. It should be nx, right? Nx again is, yeah, nx, of course, right? We're looking for the x, the power part, right? So again, n next x. Okay, now let's see if this is actually, if this fixes everything, or maybe not. Okay, and again x to the, oh, I keep it. Which one should be the power, x or n? X, n should be the power, right? Yeah. Okay, let's go back. So next n, next power. Yeah, let's do this. Yeah, n and next power. Let's see if we can fix this. No. Yeah. X, yeah, x. And yeah, we check here. Yeah, okay. Yeah. We're checking n. Okay, now it looks okay. Base case. Yeah, okay. That's the problem again. Naming your variables, right? And the next now, which one is which, right? Okay. Now, at least it should work for the positives, right? It should work for positives. It didn't do anything, right? We have a special case, right? Yeah, exactly, right? So now the question is it gonna work or is it gonna fail? Well, I assume these two will work, right? Right? Probably. I like your trust in me, right? Yeah, probably, right? But these we are not sure yet, right? Well, is it working? Assert. Oh, it worked actually on this case, but didn't work on this case. So, on assertion error. So what did happen here? Okay, you see this is what's happening. If you're trying to adjust it, micromanage this, right? So it worked on -1, right? I wonder what the negative. So it looks like it works. So, but this one doesn't work. So what does it give you? I wonder. What's the answer? See, that's why assertions are important. 1, not. It should be 0.025, right? Yeah. Okay. So let's see what's happening here. I think it's doing too much of reversal, right? I think maybe too much. Okay, let's try one more. I'll add also full power 2 to the -3, right? And let's see what happens with 4. Yeah, 1, 2, 4. It's not doing it correctly, obviously, right? It starts going upwards again, right? So not so easy, right? Maybe we'll just give you. Yeah.
No, the screen bugged.
Oh, screen bugged?
No, it's fine now.
That's fine. Okay. So now we don't have too much time to talk. We have time still to fix this. Maybe I'll leave this to you as an exercise. Maybe that's easiest for me to do, right? Yeah. To make it yourself. But yeah, of course, and also because we're still not finished, because afterwards we want to check this partial. If it's a floating point part, we want to just do it. Let the computer do it, basically. Pass the back to the computer. But of course, the question is, we could just let it do everything. Of course, that's also right an option, right? But we're at least getting closer. Now, I personally would like to fix this. I still have hope I can fix this. Now, what I'll do is I'll add again my favorite approach, verbose, right? It's true. of course, I could also use a debugger. That's another option. That's also a very good option, right? But I'm from the school of printf debugging, right? There's two schools of debugging. One group likes to use debugger exclusively, right? One group likes to use print, right? I'm more towards the print. Of course, I'm pragmatic. I realize there are times for debugger, but usually just print is enough, usually. So let's do a print. So I'll add it here, right? If verbose. So we'll see where the problem lies. This also alludes to the problem how if you mess up with this recursive step, how it can get pretty tricky to debug this type of recursive program. If you have a simple way of reducing, like, you know, go down, you have base case, right? Everything works fine, perfect. Now let's see what happens. Now, okay, 8, 4, okay, that works fine, that works fine. And now, indeed, computing 2 to the 1, 2 to 0, 2 to minus 1, 2 to the 0, right, and 2 to the, yeah, so that looks fine. Looks like this is a problem. It should have also 1, right?
Yeah.
That's a problem, I think, right? It's skipping the 1 step, right? Yeah, and it goes down immediately to the 1, right? So we found our problem, and it appears it's like in trying to fix our negative, we sort of skipped a step. So let's see how could we. So basically, in order to fix this, what I'll do is I'll make a simple loop. Go back to loops and check what happens. Let's see, division. Let's for n. Exactly. No, I don't want that. N in range. I don't know. Minus 10. And you know, I guess. Let's say I don't know 4. Printf. See what's happening here. And is. Yeah, let's take a look. Let's take a look what's happening. Oh, well, of course, n. Right. Okay, so minus 5, minus 4, minus 4. Okay, so this is a problem, right? Right, so we skip this part here. We should, if we divide by 2, it should be minus 1, right? The problem is not, yeah, okay, all right. So what's the problem? We don't want this part here, right? However, we want this part here for the odds, right? So that's the thing. Odd and evens are depend. So again, if we want to, so this is where we get the wrong step basically, right here. So if you divide minus 3 by 2, right? We don't want minus 2, we want minus 1, right? However, if we divide minus 2 by 2, we do want minus 1, right? So this looks like the easiest way I can see to fix this, right? Yeah, well, basically I need to check the oddness again. I'll do it. It's not here. I checked it here already, right? But I'll do it here already again, right? It looks like you could optimize this probably, most likely, almost certainly. So let's check. So we need to actually check. Let's check if. So basically, only. Yeah, we want these two. So basically, if and. Yes, and equals, well, it's 1, right? Equals 1, same thing, right? Yeah. Yep. Okay. Now we should be getting closer to the solution. We might still have some problems, but this might be already close to our solution. Please tell me it's still not working. Okay. It's still not working. Now let's test. At least we don't have infinite loop. I'm curious what is going to give you the answer. Yeah. Okay. Yeah. Were both false? I don't know. Okay. So 420625. That's very interesting. Look at this. This is, well, this is looking, well, not, it's not quite, is it actually, is that correct? 5 to 5. 5 is, square root is, I mean, reverse, so.
I think it is, yeah.
Yeah, that's kind of funny.
This is correct.
That is correct. but these two are not correct, right? Yeah. Very interesting, right? So, yeah. So it's not, so I think the solution lies in passing this negativeness, do it only once. I have a feeling what's happening, it's doing too many times, because if this negative number persists, it keeps going back and forth, basically. Alternating between passing it around, basically, this value, right? Ping-ponging the ball. Okay, so this remains to maybe I'll assign as assignment, but probably not. Maybe. Do you want it? I think you can fix it, right?
It's an optional.
It's an option. Oh, maybe option, yeah. To do, fix me, make it work with negative numbers, and fix me, make it work with floats. Okay, right. So let's move on to, we have 10 minutes. Again, we digressed a little bit, right? So what I'll do is also, I can do a little timing here, right? I can do a little visualization, right? The issue with this is, of course, I'm basically going to plot these times, basically, right? How fast the computer, the power works. Unfortunately, right, we can seconds time and show you, yeah, time, yeah, and so on plot running time, power, and we will see a little plot. Basically, I passed the plot results. We'll see if we actually have any results. What the time? Basic power and power, and from 1 to 50,000. Okay, yeah, all right, yeah. But at least you can see the thing. Okay, all right. Again, why are these spikes? Because I'm taking only single measurement, right? So it's not very precise, because the CPU might be busy with other things at the time, right? This is not smooth because not like time it function. I'm just taking one measurement, right? But you can obviously see how basic power, well, it's like almost linear. On here we see it looks like almost flat, right? Time is a flat circle, right? But no, it's actually logarithmic, actually, right? But you can see, obviously, you can see this basic power is much slower, right? So this leads to us to, of course, one of my favorite sites, Bigo cheat sheet, right? You can see here, yeah. Right, so here, right, so ON, actually that is ON, and we are, the good part, O log n is that's where our basic power actually is there, right? So again, one of the takeaways from this power function is that my power function actually is roughly the same as the official one, actually. It's just that it's written in probably lower level language, but actually does about the same thing, basically, right? So and I don't think you can do much better, actually, than that. Same complexity, right? So now, what else can we do today? We could do more granular. I don't know. We can actually see this, right? More graph again. But here, if you go down to, if you try to make this graph or something too tiny, your CPU, again, this overhead, this getting out of the bed cost will interfere, and you won't see anything meaningful, right? You'll see something like this, basically. Now, let's do one more case. Yeah, of course, factorials, right? Let's do factorial, right? You know what factorial is, right? So factorial of 3 is what? 6. So 5.
120.
Okay. 7. No, I forget 4,000 something, right? Because it's 620 plus 7. 4,000. No, oh, no, 5,040. 5,040, right? Yeah. Okay. Yeah. But after 8, I don't know. 8 is a lot. Yeah. 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 40,320, right?
Yes.
Yeah. Okay. All right. But okay, of course, that's why we have computers. We don't have to calculate anything after that, right? We don't live in the 19th century. So function, it's same approach, right? So base case is 1, right? For factorial, actually, so here we're kind of very extremely safe. If somebody gives you minus 500, we'll give them 1. It may not be completely correct, but it's safe. It's not going to break anything. Also 0 and 1. So 0 and 1, factorial of 0 is considered 1. For mathematical, I guess in mathematics it's considered, I guess, a reasonable compromise. Sometimes they just come up with things not to make, I mean, it's a human construction basically, right? Factorial, right? So, okay, they say, okay, for 0, it should be 1. I don't know, there's some justification for that, but out of 1 it makes sense, it's 1, right? And then the rest is simple, right? Yeah, and so, yeah, it's 1, right? Now, obviously in Python, of course, everything is built in, batteries included, right? So we can do it, we can compare it, right? 5040, so let's check our math factorial 8. Yeah, let's do that. Yeah, it is. Okay, right. So, and of course, we also have a loop solution, right? Or what I call a top-down solution, right? We start, of course, when you're doing multiplication, you should start with 1, not 0, right? Sometimes you multiply things, you put 0 somewhere, what's going to happen? You end up with 0. Yeah, you get up with 0. You get a big fat 0, right? So, so we start with 1, and of course, this is a loop solution. So let's compare these solutions, right? We have a top-down solution, right? We start. Jimmy? Somebody had a comment? No? No? Okay. All right. So top-down, right? And also, we could also compare it with a go up, right? Loop bottom up, right? Meaning start from 1 and then keep multiplying things, right? That might make a difference, actually, where you start. So this one here is closest to the this one here, right? Unfortunately, we don't really have a good way of optimizing, not like this trick here, right? Basically, they're all going to be roughly the same, right? Maybe if you read some scientific papers, maybe somebody has some cool things to do on factorials, but we don't really have a way of optimizing, right? We have to keep multiplying all the numbers, right? We don't have any tricks, any cool tricks. It's going to be linear, I think. But let's see. Let's take a look. Yeah, factorials. It works. We have a, yeah, it works. So let's do our factorial of 10. (800 nanoseconds). Okay, so I expect it should be roughly 10 times slower, so about 10 milliseconds, I don't know. But again, there's going to be overhead because what factorial of 100 is pretty big, right? It's going to be like that again. So you run into this problem, you see. No, it looks, it's roughly about 14 times slower, well, 15 times slower. But yeah, there's overhead again. Sometimes this complexity, one of the takeaways from today's lecture should be that sometimes this complexity hides somewhere where you're not looking, basically, right? You have your algorithm, right? But you're dealing with these huge numbers and, right, basically the storage requirements, things like that. Actually, there might be some hidden complexity somewhere else, basically, right? So even some simple operations. You need to also sometimes, if you test it and see something getting slower, right, you might want to check some basic operations. Maybe something else is slowing you down, not the algorithm itself, right? So 10 and 100, and now we'll check it if it's actually loop one is better, right? And actually I think it's going to be slower. Let's see, bottom up, 100. Oh no, 100. Roughly same, and top down. Micro. 9, yeah. So top down, starting with a bigger number, slows down things. So if you build up, it's a little bit faster, right? Because they got to the big numbers quickly. Basically, that's the only issue, right? Memory was just, at the issue. And now let's do this for 100. No, math factorial. I want to do math factorial. Math factorial 100. I want to see what the official one, how fast is that? I want to see. It should be, it might have pre-built tables, there might be some optimizations. I want to see how badly it will beat OR factorials. Maybe it actually won't. No. Yeah, it beat it. But not too bad, actually. Not too badly, actually, right? Again, because probably it's written in C or C++, right? And it's just being a calling there, but actually, right, it doesn't spend as much time in Python land, basically, right? But it doesn't look too bad, right? So 10, so 1 microsecond. I don't know, do we want to do 1000? Let's try this, that's a big number, right? Let's do, we have, like, then we can go to the break, right? So let's do 1000. Actually, I did it before. Okay, let's try it. So 400 microseconds. So yeah, again, it's slowing down more than we expected this linearity, right? Because again, why? Because we keep increasing these numbers are getting huge. The factorial of 1000. How many zeros are there? I don't know. It's huge. Do we really want to print it? I could print, if I print 1000, it's gonna be, I don't know, I can do print 100, I could probably do 100. So bottom up, so top down, bottom up, should be faster, a little bit, right? A little bit, not maybe, again, within the standard deviation, but slightly, still on mine, 1000. Yeah, 15 max, so about 8 times. It's getting a little bit better. So how about our own factorial, right? Factorial, right? And I think it's going to be, the recursive solution is going to be slow. Let's take a look. Yeah, 500, but no, not, okay. So roughly within the same, so our loop solution is a little bit faster, right? Because it doesn't have to keep all these function calls in memory. Yes, question? Oh yeah, you could, of course you could just do the empirical one, right, see what's happening during this call, right. Probably a debugger would be one option, or you could just do, of course, Process Explorer, of course, you could see this, cheat a little bit, right, that'd be one way of doing it, right, just a quick and dirty way, right, but there is a way of doing memory profiling as well, right. I don't know if you can do it here immediately, right, but you can, actually, you can do it, yeah, you can check. So, because of course, they have to release this memory afterwards, of course, right? So, because of course, Python has built-in garbage collection, right? If you're not using it, then it goes away, right? So, what else? I'm not going to do any more factorial. Okay, factorial 5000. There it is. Look at the end, right? All these zeros, right? What's the story with factorials? You get 0 every, to 2, 5. 2 times 5 is 10, right? That's 1 0. Then tens. When else do you get zeros? You have 25 and 4, right? That's the same thing as 2 and 4.
I suppose after 10 we got simply every 5, also 15, 20, 25 we got, because we'll have one after 10 already 0, so
yeah,
like 100% give us another.
Yeah, because 25 and 4 will give you one extra 0. Yeah, it will give you extra 0, and then 125 and 8 will also give you a 0, and so on. And is anything else give you 0? An extra 0. There's a way of calculating how many zeros you expect. Even if you can't calculate this number, this was Olympics question a long time ago, how many zeros you get in a factorial, right? So you can calculate how many zeros are there actually without knowing the number, right? You can cheat there a little bit. Okay, yeah, 16,000 number. Okay, what else I was going to show you before end? Yeah, you can check, the speeds. There's some graphs. Yeah, Fibonacci, but yeah. All right. So, what's the takeaway from today's recursive calls? How do you solve the problem?
Base case.
Yes.
And then reduction.
Yes, that's it. That's easy, right? So just keep in mind, it might not be as efficient as you want. Later on, we will see actually how to calculate this complexity. That's in a couple lectures, right? So, all right. So do the quiz, which you're gonna do it now. It's easy, right? And we'll see you in about 25 minutes at 11:10.
Yep.
Yeah.